How do you troubleshoot parasitic capacitance and inductance in designs? Imagine you're trying to get a clear signal in your electronic circuit, but something keeps causing interference or distortion. That sneaky culprit might be parasitic capacitance or inductance. These are unintended electrical effects that sneak into your design because of how components and traces are laid out. They can cause signal delays, ringing, or even data errors. Troubleshooting them is like detective work, but with some straightforward steps, you can track down and fix these issues. First, understanding what parasitic capacitance and inductance are is key. Parasitic capacitance happens when two conductors are close together and have a voltage difference, forming an unintended capacitor. This can lead to signal coupling or crosstalk, especially at high frequencies. Parasitic inductance, on the other hand, comes from the physical shape of your traces and components. Long loops and leads create inductance, which can cause voltage spikes and ringing during switching. Next, look for signs that parasitics are causing trouble. You might see distorted signals, unexpected oscillations, or increased noise in your measurements. Digital signals may overshoot or undershoot, and high-frequency circuits could show reduced bandwidth or resonance issues. In analog circuits, low-level oscillations or shifts in gain can also point to parasitic effects. Using simulation tools is a smart move. Electromagnetic and circuit simulation software can model how your layout influences parasitic capacitance and inductance. These tools let you see how signals behave with different layout choices before you even build the circuit. You can tweak trace lengths, component placement, and ground planes in the simulation to find what reduces parasitics. Measuring your actual prototype is equally important. High-frequency oscilloscopes can reveal signal anomalies, while network analyzers help measure impedance and identify parasitic elements directly. Time-domain reflectometry can locate where reflections and impedance mismatches happen along traces. Comparing these measurements with your simulations helps confirm where parasitics are causing issues. When it comes to fixing parasitic effects, start with layout changes. Keep traces as short and straight as possible to cut down on inductance. Avoid sharp corners that increase impedance. Place sensitive analog or low-level signals away from noisy digital lines to reduce capacitive coupling. Use ground planes and shielding to provide low-inductance return paths and block electromagnetic interference. Choosing components with low parasitic parameters, like ceramic capacitors with low equivalent series inductance, also helps. In your printed circuit board layout, increase spacing between parallel traces to lower parasitic capacitance. Use controlled impedance traces or coplanar waveguides for high-frequency signals. Minimize the use of vias and stubs, which add parasitic inductance and capacitance. Proper soldering techniques ensure good connections and reduce parasitic resistance. After making these adjustments, run your simulations again and test the physical circuit. Check if the parasitic effects have been reduced enough to improve performance. Keep in mind that sometimes a small amount of parasitic capacitance can be beneficial, like in decoupling capacitors that stabilize power supplies. By combining a solid understanding of the basics, careful simulation, precise measurement, and thoughtful layout, you can troubleshoot and minimize parasitic capacitance and inductance. This process helps improve signal integrity, reduce noise, and make your circuit work just as you intend.